once we get our remaining points up for this random distribution of scores to seats, because this was random assignment, right? We're trying to see if there's actually a relationship between the row that a student sits in and the score that they get in the class. We had a slope that indicated there was this negative relationship, but we don't have enough information from just that one set of class data to determine whether this is a cause and effect relationship. So we went through, we did several simulations. That's what our dot plot is here. We've got the simulated slopes. How could I use this simulation data to try to determine if this is actually statistically significant? What did you say? We're looking at, if you look at it, it is kind of starting to take on a more normal shape. It's got kind of these two bumps in it right now, but we don't have any large outliers or this horrible skew going on. So we do have some normality here. When we've done confidence intervals and when we've done hypothesis testing, what do we always calculate? Sorry, specifically with hypothesis testing. The p-value. What is the p-value telling us? Think about the way we write this out in our conclusion.
The probability of getting the X bar or whatever.
Yes, it's the probability of getting that result or greater, getting that result or smaller, purely by chance. So I want to kind of look, does anybody remember what our observed slope was? What did you say? Our slope. Super close. Negative 1.517. So we had this slope that had a negative 1.517. If I was going to put that on the graph here, I'm going to have to kind of ballpark it, but let's be generous. Let's say that that's about there. And all of these over here are smaller than negative 1.517. Were you able to get your slopes up yet? Okay, wonderful. So let's count how many dots we have, and we're going to calculate the p-value of getting that or smaller. How many total dots are up here? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Looks like we have 48. How many of those are our observed result or less? Coming up with, like when I'm looking up here, I'm getting 9 because I think that's just a single dot right there. 1, 2, 3, 4, 5, 6, 7, 8. I'm coming up with 9. 9 over 48 is what as a decimal? How much? 0.1875. Think about all of the alpha levels that we could be using to compare this to. It's greater than all of them, right? So do you think our result is statistically significant so that we could say that sitting in a closer row gives you a higher score, sitting in a farther row gives you a lower score? No, we would reject, we would fail to reject our null. And our null hypothesis, if you remember up at the beginning, this was that there was no impact. Let me take control of this and go back there. Our null hypothesis was that the seat location has no effect on exam score. Since our p-value is greater than all of our possible alpha levels, we would fail to reject. The probability is just too great to happen purely by chance. Something I want to explain quickly before we move on to, I wrote out the null hypothesis like this. Null hypothesis is that beta is greater than 0. Beta, remember we had b for our slope. Beta would be the true slope of the population least squares regression line. B is our observed slope, but beta would be the true slope. I want to show you guys, we can use some technology to do these simulations rather than having to do them with the cards. So I took all of the information about the rows and the student scores and I entered it into Stapplet, which we've used in here before. So I put all that information in there. It calculated, here's my data. So there's my scatter plot, there's my least squares regression line that we did. Do you guys remember talking about residuals? Residuals is kind of how far away we were. So there's my residual plot. We'll talk about that here in a minute too. But then I can come down here and I can perform inference. That's what we do when we calculate confidence intervals and when we do hypothesis testing. That is called inference. So I'm going to do an inference procedure for the simulated sample slope. And I'm going to do 100 samples. We only had 48 in here. I'm going to look at 100. What does that look like? So there's what the dot plot would look like if we had 100 samples. I can add 100 more so that we're up to 200. 300 simulated samples. As I take this higher and higher, what are you noticing about the overall shape as I collect more samples? It's getting more and more normal. There it is at 1,000. I can use this to kind of shortcut having to do it out by hand. I can even then take this information and figure out exactly how many of these simulated samples have a slope of negative 1.517 or less. So I've got count the number and percent of dots less than or equal to, and I'm going to enter our slope right here. Negative 1.517, and I'm going to hit count. So it's showing me that result there. It says there's 133 dots, or 13.3%. What did we calculate it as with our p-value? 18%, 19%. So we weren't too far off when you're adding more and more and more and more samples. So even adding more samples, we would still fail to reject the null. So far, so good? All right, let's get our important ideas down for today, or for yesterday, actually. Sampling distribution of B. So statistics versus parameters. The y-intercept, the statistic, the observed y-intercept for the least squares regression line would be A. The parameter for that would be alpha. The statistic for slope for our observed data least squares regression line would be B. The parameter would be beta. The standard deviation of the residuals is S. The parameter is sigma. We've been using that notation previously. Standard deviation of our residuals is S, and the parameter is sigma. The standard deviation of the slope statistic is SEB. The parameter is sigma B. If I could collect all of the population data, if I had access to the entire population, and I could calculate the least squares regression line for the whole population,
that would be mu y equals alpha plus beta x. When I calculate a least squares regression line from just a sample piece of data, it becomes y hat equals a plus bx. You guys noticed this as we added more and more and more samples, it became more and more approximately normal. The sampling distribution for our slope, sampling distribution for B, is approximately normal with a mean of 0 and a standard deviation. If I had the population, that would be sigma B. If I don't have the whole population, if I'm having to estimate that, that's SEB, standard error of B. Once you are done copying this down, I want you guys to look down at the check your understanding. Read that paragraph there, and then look at the Minitab data. Minitab is a statistical piece of software. What is printed down below that paragraph is what Minitab data output often looks like. We've seen this before on some of the homeworks, but I want you guys to go through, find the estimate for alpha, find the estimate for beta, find the estimate for sigma, and then give the standard error of the slope. And then I want you to interpret all of those values. What are the independent and dependent variables here? What are the x and the y? Age and ear height. Which one is the known piece of information, the independent variable, the x? Age. And they're using that to try to predict what? The ear height. So age would be our x, ear height would be our y. If you're not sure from the information given up above, they tell you that x variable right here. So they've given us some different information in this Minitab output. When they refer to it as a constant, what are they telling us? Stays the same. Which part of this equation would stay the same no matter what? The a value, right? It doesn't have a variable next to it. So what are they telling us here? They're giving us our a value there. A value is an approximation or an estimate for which parameter?
Beta. Or no.
Alpha, which is our y-intercept, yes. So the estimate for alpha is A, 2.8871. That's our y-intercept. Graphically, a y-intercept, what does an ordered pair look like when I'm talking about a y-intercept? X is 0, and then we have this as our y value, right? What does our x variable mean here? 0 years. So if I'm going to try to interpret this y-intercept in context, people that are 0 years old, or newborns, right? What are we predicting? Because remember, least squares regression lines are just predictions. Yes, sir? Yes. For people that are 0 years old, for newborns, we predict, really important to include that word predict anytime we're talking about a least squares regression line. We predict their ear height to be 2.8871 centimeters on average. Part B says, what is the estimate for beta? Beta is the parameter for what piece of information? Slope. What's the statistic for beta? B is my statistic for beta. Where is that shown in the table? Right under A. They have age here. That's going to go with my x variable. And the coefficient that goes with that, so the number out in front of my independent variable. So here is my value for B, 0.0021. So B, 0.0021 is my estimate for beta. That represents the slope. How would I interpret that slope in the context here? Yes. For each increase of 1 year in age, or for each additional year, we predict the ear height to increase by 0.0021 centimeters. Absolutely. These other pieces of information that I have labeled up here, it says SE coefficient. Well, here's where I have A, the constant. SE, that would be the standard error for A, which is not one of the things that we talked about up above, but we did talk about the standard error for B. That is this piece right here. Oh. Why is that not moving? I don't know why it decided to do this, but this is the standard error for B. Down here at the bottom, S, what was that the statistic for? What is that estimating? Standard deviation of the residuals. This is the standard deviation of my residuals. This is the standard deviation of my slopes. We're not going to use the standard deviation of the y-intercept, but we will talk about the standard deviation of the slope and the standard deviation of the residuals. I am not going to ask you guys, AP will not ask you guys to calculate the standard deviation of the slope or the standard deviation of the residuals. That will be given to you in output that would probably look fairly similar to this. What else were we supposed to find the estimates for? C and D down below. Sigma. What is the estimate that we have for sigma? S, the standard deviation of the residuals. So 0.3613. Standard deviation of the residuals. Does anybody remember how we would interpret that? Talk to me about actual ear heights. Would everybody follow this exact predicted pattern? So typically, what could we expect? Yes. Actual ear heights typically vary by about 0.3613 from the predicted ear height. And then the standard error of the slopes, SEB, 0.0059. That's the standard deviation of the slope. How is this different from this? How is the standard deviation of the residuals different from the standard deviation of the slope? We said that the standard deviation of residuals meant that actual ear heights typically varied by that amount from the predicted ear height. That's what my residuals are telling me. But this is the standard deviation of the slope. So what would be varying? Would it be ear height? It would be the slope. The slope of our least squares regression line typically varies from the slope of the population least squares regression line by about 0.0059, and then I need some context in here, centimeters per year. Standard deviation of the slope, or SEB, tells me typically the slope of my sample least squares regression line, how much that typically varies from the population least squares regression line, or the true least squares regression line. right, go ahead and once you've got this, turn the page. We're going to keep looking at the same data. If you need to grab a quick picture of what's up on the screen, please feel free. I'm going to switch over to the next page. So the first thing that we want to get written down here, we want to recopy our line of best fit, our least squares regression line from the original sample data, 85.95 minus 1.517 times the row is equal to score hat. The slope B was negative 1.517. And the standard error of B was 1.33 from our computer output. And I can show you where that is in Statlet. If we were to take another random assignment of 30 students, would the slope of that least squares regression line be the same as this slope? Why not? It's going to vary, right? When you guys calculated the slopes for your random assignments, we didn't all come up with the exact same slope of negative 1.517. Every random assignment is going to give different results with a new least squares regression line and a different slope. We're going to learn how to construct a confidence interval for the slope of the population least squares regression line. If I want to construct a confidence interval for the slope, what is my parameter? Beta. And what would beta represent then? The true slope of every least squares regression line? Think about parameter. Parameter describes what? Sample or population? Population. So beta is what we would be trying to estimate, and that would be the true slope of the population least squares regression line. What's the statistic that we have to work with? What did you say? 30. That's our sample size. That's important. If I'm trying to estimate the slope, I'm trying to estimate beta. B is my statistic. What is our B value? Negative 1.517. Yes. Before we go on and talk about the conditions that we need to check, I want to show you this data in Statlet. So same data that I showed you guys before when we did our simulation. I have all the data entered into Statlet. It gives output that looks a little different in form than the Minitab output, but it gives me all the same pieces of information. When we talk about our parameter, it is not just enough to say true slope of the population least squares regression line. I have to include some context. What is my independent variable? What is my dependent variable? For row, that's my x variable, and score, that's my y variable. I'll pop this right back up in a second. But looking at this data here, so there's all the data that I entered, scatter plot and least squares regression line for our data. Right down here, I'm I'm going to click on include more detailed regression output, because here I have my equation, I have n, it tells me s, it tells me r squared, but it doesn't give me the standard error of b. Now it gives me the standard error coefficients for my constant, for my row. There's my standard error of b right there. Hopping back over here. Conditions that we need to check. There are 5 conditions when we do confidence intervals for slope. Normally we're used to checking how many conditions? Just 3. What are the 3 conditions that we normally have to check? Random, independence or 10% condition, right? And normality, which we get to by large counts, or that was our chi-square large counts. So do I have to check those here? Yes. In addition to the standard 3, I also have to check that the scatter plot shows a linear relationship. Let's go look at our scatter plot here. If I were to take that line away, it's kind of all over the place, right? But it doesn't necessarily show a different shape. It doesn't look more like a parabola or more like an exponential. So it has a very approximately linear shape to it. Very approximately. One of the other things that I can do to check the linearity is look at the residual plot. As long as it doesn't have a leftover curved pattern to it, then I can say that that scatter plot has an approximately linear relationship. So if I look at that residuals plot, do we have any kind of a curve there? No. If I had all of my residuals above and then below and then above so that it had a U shape, then I would say that this is not a good fit for a linear relationship. But as long as my residuals plot doesn't show any kind of leftover recognizable pattern, then an approximately linear relationship is appropriate. Independent. It's normally my 10% condition, right? Think about this situation. What did the teacher do in this situation? Were they doing sampling without replacement? They did random assignment. Do I need the 10% condition if we're doing random assignment? So in this case, I don't need 10%. Not sampling without replacement, each observation is independent of the next. If I'm doing random sampling, then to check my independence, I would need to check my 10% condition. Checking independence. To check normality, I'm going to look at the dot plot of the residuals. It can't show a strong skew or outliers. Does the dot plot of the residuals show a strong skew or outliers? Then we would say it's approximately normal. It asks you to make a quick sketch of that. Show the dot plot of the residuals. To check our fourth condition, we're still looking at the residual plot. If this residual plot right here has roughly equal variability at each of my x's, and by roughly equal variability, I mean that this one is about as variable as this one is about, and again, I'm looking at approximately. How I would know if it was not is if I saw like a sideways Christmas tree pattern, where it starts off really close to that line, and then it's further away, and it's increasing in variability as I move through those x values. So it's going to have a sideways Christmas tree pattern if we don't meet condition 4. Did you guys get your sketch? All right, I'll have it up in the notes later if you need it. So we want roughly equal variability at each x value. We're going to end here for today, random. Do we have our randomness condition met? Yes. Where were we given that? Random assignment, yes. Teacher used random assignment, so we have our randomness condition met. Got this little acronym to remember all 5 of the conditions that we need to check. Liner. Kind of sounds like linear, but we don't have the A. So we check that it's linear. We look at our scatter plot. We also look at our residuals. Independence, normally that's going to be our 10% condition unless we have random assignment. Normality, we look at our residuals. Equal standard deviation, we look at our residuals, and then randomness. We will finish this one up tomorrow and start the very last piece. Also, I mentioned this before spring break. I meant to remind you guys yesterday, but we got to the end of class and I forgot. Mock exam for this class is Thursday. Mock exam for this class is Thursday. Take this as an opportunity to not just practice getting ready for that AP exam, but making note of some of the things that you're like, ooh, I don't remember that part. Those would be pieces that we absolutely need to make sure that we hit almost 3 weeks that we have between the time that we finish this material and when you actually take that exam. We're going to have like within a day of 3 weeks to review for that. So we should be able to help with that. We're going to be, I believe, in the cafeteria. So we'll be with the other statistics class, and we'll be in there, I believe, with Calc AP and Calc BC. So like all of the math AP exams are taking place. It's going to be periods 1 through 4. 1 through 4. So this Thursday, periods 1 through 4.
Right after each other.